It would help if we had a screen, huh? All right. We have like a couple more seats up here where you're within like grabbing distance, so I can really get you. So far on Husky CT, there's just one link up there. So throughout this next week, I'll fill out the rest of like the schedule and all the assignments and readings and all that. But to start, we just have syllabus. I think syllabus is usually a pretty good way to start. We got 14 weeks. Well, 15 if you include spring break. We got time. We can do this. Everybody knows what class they're in. What is this class? Big picture. What are we doing here? Mechanics. Okay. Yeah. Dynamics. Yep. So we had like mechanics 1, which is very much like nothing move. Make sure nothing is happening. Buildings, bridges. Now we have dynamics where it's like, all right, I want it to move. What's the extra tools that I have now? So now I've got momentum. I can change momentum. All sorts of that good stuff. That's what we're here for. I'll make sure that we're all caught up. There we go. Okay. Nope, don't need that. Just want to zoom in a little. And usually my link is right up at the top, but that's okay. Okay. All right, so I'm Professor Ryan Cooper. Right now we're watching, so you're watching me stream the YouTube lecture so that it is recorded. There is that database of like stuff that you can go back to. And then, yeah, then there's like a link down here in the course live streams and video. So you can always go back to like previous lectures. For the most part, we're gonna come to class and work on problems. Some people, it really helps when people like come to class and work on things and ask questions and talk to each other. Some people can't make it to class, so it is always streamed. It's a very different experience if you're watching like online lecture versus being here in class. It works for some, other people. It's the only time when I started streaming, it's the only time that people said, man, I wish I was in class, because they like watch the video, see people like doing stuff, and then at the end of the semester they're like, oh, maybe I should have gone like instead. But it's up to you. You are adults. This is your class. However you want to participate in the class, that is up to you. We'll get to that in terms of like participation for the course. Yeah, we'll get there one at a time. We have like our course discussion is GitHub discussion board, and like a lot of times, especially like in person class, if we're in person doing work together, a lot of the questions get answered in class. So sometimes that gets used more or less. If you're working remotely, then then the GitHub discussions is a great place to like get some feedback from other people also working remotely. Then Husky CT will be our main like submission for assignments and all of that, and all the course resources are kind of organized there. But this website it's an open website. You can like copy it, make it your own, and kind of redistribute. And this has a lot of like the readings, videos, and those kind of things. And then we'll be doing some Jupyter work, and it's called NanoHub. They offer computational resources for all sorts of engineering and science kind of work. Have you used Jupyter and Python before? Some yeses, some nods, some like, what the heck are you talking about? Knows. A little bit. Cool. I love Jupyter. So this whole website is built with like Jupyter and Markdown notebooks, and I think it's an awesome way to organize like thoughts, ideas, and models. So like if we jump into, yeah, the first thing that we'll do is like homework 0. Some reintroduction to Python, but then also some we can do like modeling free fall, like projectile motion kind of problem. We can graph it. We can say, all right, well, we threw it, started at 1 meter. When does it hit the ground? Do some logical operations and figure out, yes, it spent about, what was it, 3.3 seconds in the air, and it was 0.6 meters from the ground at the end of that. You can do some cool, different way of approaching problems, but similar ideas. Like, have a model, I want to use it to actually engineer something. And logistics stuff, it can be kind of boring to start, but it's kind of like why we're here. It's like, what are we doing in this class? For us, except for me. Maybe. Big bird. For class? Yeah. All right, come on in. So it was for me. So coming back to like main page, if you see at the bottom of every page, my name is in blue. You can click that link to get to like scheduling office hours. So it has like my main office hours link for Calendly to try to help us like match up schedules. My YouTube channel, so you can get to videos of this class, other classes, where I am, what building I'm in, and then all the other courses that I've been working on over the years here at UConn. No issues so far. So far, it's just sort of like identifying resources. It's all like pretty quick, but we recorded it so you can watch it in 1/4 speed and slowly get through all of this. All right, so let's jump into like the actual, like what are we, it's weird. Why did it added one extra row? Final, I guess that one sounds important. It's its own row with no grade, no requirement. All right, so main structure of the class. Participation is a fifth of the grade, but this grade I leave up to you. So one way that you could say like, hey, I'm getting an A in this course, kind of roughly, I showed up to 90% of the lectures. Like, that's pretty good. I was talking to other people, working on questions. Maybe you weren't the first one like answering questions, but maybe you kept notes and you compared them with other people in the class. You can say like, yes, I should have an A in this class because I did all those things. Or if you're using like discussion board, like if you're posting things on the discussion board and or answering questions, that's another way that you could say like I was active online. Or also like watching the videos and keeping track. Or if you're, one thing that's super helpful is like people have posted just things that help them do work. So like I've seen posts go up of like, hey, at minute 38 in this link to this YouTube channel, to this like YouTube video, there's a great like more in-depth step-by-step for problem 3 on homework 2 or something. Like that's amazing, and it helps so many people, and it helps you kind of organize your thoughts. Like, how do you communicate? Like, what are the problems that you're identifying? How are you communicating solutions that way? So that one, halfway through the semester, you'll submit like a work in progress participation grade of just where you think you're at. And if you're fine with that, you can say like, I'm a B and I don't want to participate anymore. I'm going to stay at a B. That's okay. Or you could say like, I feel like a C. I just don't know what to do. Something. Can you give me some help? And then we can revise. And then at the end of the semester, put a new grade like A, B, or C on participation. Homework, again, we'll do most of those like in class. We'll be working on homeworks in class. Last semester, I explained what a flipped classroom was. And then I asked if people had questions, and like, we've done this before. I'm like, then why'd you let me describe a flipped classroom for 10 minutes? Like, if you already knew, like, you can always stop me and be like, we already know Newton's second law. Like, we can move on, or you can always stop, like recheck. It's your class too, right? What content we want to get through and build. So anyway, we'll do that in class. Like a lot of the homeworks, we're kind of going to go through like one at a time, talk about what does it mean, how can we use it. Then at the end, after we do the homework, that's the time to think about like how can you demonstrate that you understand, like what's another application that would demonstrate that you understand whatever learning objectives we were working on. And we'll build the quiz together. So each module will have a quiz. At least the first 4 modules will have quizzes for. And then you'll go home, do the quiz, and then turn that in online. So that one's like on your own time quiz. And then projects, we'll come back, look at the projects that we're going to work on. And a lot of those will be Jupyter notebooks, like 3. We'll have 3 notebooks where we'll edit things. The goal is not to become like proficient Python Jupyter programmers. The goal is be able to read and interpret engineering ideas that are inside Python code. So if you're hitting a wall, or like one example would be like, I know I want to plot something. Like I want to look at kinetic energy. I just don't know how to do it. Then that's something like I'm happy to like give you the line of code that plots kinetic energy, and we can identify like what we're trying to do together, something like that. So that's like the level of Python understanding that we need. When you see it, you kind of roughly understand this is what it's trying to do. So it's not too scary. And after you do that, believe it or not, you'll be proficient Python programmers anyway. So we don't have to go in hardcore. And then the last thing that we'll do, we'll save the last 2 weeks of the semester for like an independent research project. Of module 5 is a rough draft and a final draft of something that you think is important for dynamics. This is different for everybody coming to class. Like aerospace is a big manufacturing here in Connecticut. Also, we have electric boat here. And then there's all sorts of other things and like hobbies and stuff. Some people, I'm trying to think of the things, like mountain biking has come up a few times for final projects, aerospace applications and like flight pads, but identifying something in dynamics and how you can apply this to either something that you like or your career or even like a Spider-Man comes up. I think because I like Spider-Man so much and people are like, oh, I'll get an A if I do like a Spider-Man project. I don't know if that's the key or if it just really resonates, like Spider-Man, because he is a cool superhero. It's like the ADD Marvel superhero that I love. But yeah, looking at like what are the physics of Spider-Man stopping a train, like something like that. And yeah, module 1, the project is identifying what you want to do in module 5. The reason for that is like I'm big on learning as a journey sort of metaphors. Like that's you're like going into this cave, and that's that guiding light at the end of like if I understand this material, I can get out of the cave with like a Spider-Man physics story, right? Like that's like something guiding you, your compass, in like Legends of Zelda. That's like when you can actually make your way through the map. You have a compass. Like, all right, if I can do this, now I have that Spider-Man model, and it's going to be awesome. All right, so that's a lot of objectives. Take a second. We talked a little bit, so we know this is like mechanics and dynamics. So take a second, ask a neighbor, or you can even like write it down yourself of like, what's a reason to be in this class? I know it's required. Like none of you signed up to be a mechanical engineer and then someone else told you this is important. So if you step back from that of like, I need to check these boxes, why is it important? What's something, why are you here in this class? What's something important about it? So let's take like 2 minutes, ask someone, write it down, get an idea out there into the world. Mm, what else? Oh yeah. What else did I miss? Talked to a few people. Did that capture the groups of thought so far? Did I miss anybody? I only talked to like just small smattering. What do you think? What else came? Was there anything else that came up that I didn't? I'm like, broad. This is real broad strokes here. I'm just taking a lot of ideas and just like, how about this? What else? Everybody was talking, but it was all this. It was exactly what I just wrote. Nobody had anything else to say. Yeah.
If you wanted to be Spider-Man, you probably need to know a lot of this stuff.
For Spider-Man? Yeah, Spider-Man is like super science nerd, like, which is another part that I love about him. Yeah, so just in case, I guess like a just in case. It's another reason why we're here, like just in case. There's a lot of research going on at UConn, maybe over in like PNB. There are a lot of bugs there in the PNB. Yeah, and I heard like some ideas of like static and dynamic of like first we learned statics and now we like one person said of like, okay, let's like level up now, add motion to this problem, like make it more complicated. Sometimes it's more complicated, other times sometimes dynamic like static structures are more like if you have a big bridge and you're identifying all the internal forces in it, it's a lot of work. It's sum of the forces at every member, identifying the zero force members, and like all this, like a lot of work to do there. And meanwhile, like a free fall application, like, all right, well, there's one force. Done. All right, now MA equals MG, so A equals G, and we'll move on. Solve the problem, like problem mostly solved. So sometimes it's more complicated, other times like not as complicated. I think main thing is like how do you use and predict motion? Like so science, I heard someone say like one time it's like science is asking like like why things are the way they are, like how do I predict or how do I try to understand what's going on. Engineers kind of get a hold of it and they're like, now that we understand it, can we use this as an engine? Can I like transfer can I transfer energy through this? Like start asking questions like how do I use this to my advantage now that I have this knowledge? So that's kind of what I was thinking. It's like, how do I use? Or how do I design around it? How much time do we have? We got time. All right, sweet. How about course? So these are kind of big picture ideas for why we're here. Does the course structure line up with why we're here? Like working on problems in class. One of the things about flipped classroom is that now the reading and material is kind of on your own time. Does that feel like a good idea so far? Maybe. Does anyone want to bring up issues or questions that they have? I know there's always questions. It's just whether or not you can recognize, like, if you have it, there's 10 other people that have the same question.
So, I mean, it's obvious, but you're saying that it's basically almost completely async and then it's mostly just review in class?
Review in class.
Like, so we learn all the material at home and then we do problems in class, basically.
Okay.
Or a little bit of both?
Yeah, like we'll definitely, so let's like pop open. So like when we start up module 1, there's a few chapters in this textbook, and the textbook we have access to through UConn Library. So you can click these links, you can download the PDFs, you can print them out, you can do whatever you want. And then I identify like chapter 1's pretty short, so that one you can probably just read through in a few minutes. Oh, I don't know, 20 minutes or something. And then I usually identify a few problems that I think are like specific to this class, like these tutorials, this example, and that way. And then there's like some other readings that I kind of go through, like my thoughts on these subjects. I think these are helpful to take a look at, like give you a little bit of mix of engineering and Python work, so that when we're in class, we can say, all right, let's start with problem 1.1. We can open that and then look at how are we solving it. So review in the sense that like we're going to open up problem 1.1 and go through it start to finish. in the class. Yeah. Okay. When should it be done?
Yeah, but like, I guess like the due date for the reading.
So due date for reading, like by time the module is over, then there should, like, the reading should be done by then. Some, again, like if I was a student taking this class, I would probably do the homework then the reading, because it was just, that's the way I operated. I was always like an inverse kind of problem solver of like, try it, like, man, I don't understand any of this, and then do the reading, like, oh, that's how this works. Like it was easier for me to connect the dots. Other people like to be like super prepared, back to like video games and Legends, of like, you can either just like jump into the boss and die and then go back and grind your way up to the level that you need to be at, or grind your way until you're like totally leveled up. Like, I understand everything in this class, and then every problem you get is like a one hit. Like, haha, now I understand. Gotcha. Yeah, so that's up to you. But for the most part, like once the module's over, it's all connected. Like module 1, module 2, 3, they're all kind of building and connected ideas. So if you fall a little behind and you're still in module 1 reading when we start module 2, it's not the end of the world. But again, it's kind of like on your own time, your schedule. But if you wanted to be like prepared for every homework assignment, then it's like, as we get to class, you've done the reading up to that problems reading. Yeah. Cool. Those are good clarifying questions. Yeah.
Is there a schedule like when we should do the reading by what class, or is it kind of just like do certain chapters and we're going over chapter 1, like chapter 2 we're going over
Not that one. Here. So like in this module 1, when we're starting here, chapter 1 should just, that one you can read anytime before we start the module 1 problems. I think it gives some good background information. A lot of it's review about like, hey, forces exist. We're gonna use vectors, and like a lot of that you've probably seen before. But then these other like tutorials and equations, they'll help us do the problems for the homework when we're in class. But you can, depending on how much background knowledge you're bringing and how much experience you have thinking about dynamics and engineering problems, sometimes it's harder or easier. Yeah. Not to give like a wishy-washy answer, but it's just sort of like module 1, the reading you can do anytime as we're doing module 1. And then module 2, any readings are just happening as we go along. Cool. Do we want more stuff? All right, so we talked about why we think we're here. So then course objectives, like big picture. And it lines up with kind of what we had talked about, like why are we here? Applying kinematics and applying kinetics. And those are the two like main things in this class: kinematics, kinetics. One is identifying what is kinematics, what is kinetics, like why are they different? Why do we have two words that sound so similar that and they're similarly interchanged. What is, I know I have like some things up here, but what is kinematics? I know there's one thing that most people immediately think of. But what is kinematics? Let me walk around this way. What do you think? What would kinematics be? You can ask someone, or even look it up on your phone or anything. Yeah.
Like projectile motion.
Projectile motion? Yeah. Okay. What makes projectile motion like kinematics?
Kinetic, mathematics.
Can't spell. Kinetic mathematics? Kinetic motion. Yeah. So kinematic equations are kinetic equations? Maybe. What are there's like three main equations, right? For projectile motion. Like x of t equals x0 plus b0 t plus g over 2 t squared. V of t is v0 plus gt, and then I think like v of x equals, or v of x squared equals v0 squared plus 2 g delta x, like that, like our three things like that, at least for one-dimensional, like falling kind of problems. What is all this like saying? Like we have all these equations. What are those equations telling us? Yeah.
They're telling us the position of our object relative to time. Or like
position, yeah. So like
time changes, how does the position of our object change?
Yeah, so it's identifying like this is a position and this is velocity, and they're related, right? Like a change in position is a velocity, and a change in velocity is acceleration. So kinematics is all about like identifying motion. Like how do we even describe something that's moving? And that was it was kind of a really hard problem to solve for a long time, because motion was just sort of this nebulous, like, seems like it's moving, but relativity, people kind of understood relativity even in like Greek times, and like some people claimed motion's impossible, other people claimed like everything's always moving. And have you heard that, the Zeno's paradox? Do you know what that one is? That you can never actually arrive anywhere, because in order to go to the door, you have to get halfway to the door, and then in order to get halfway, once you're halfway, you still have to go another halfway to the door, and once you're there, you still have to go another halfway. And as engineers, it's kind of like, yeah, after three steps, I'm basically 3 half steps, I'm basically at the door, I can leave. But at the time, it was an actual like paradox before like limits existed. Like maybe motion is impossible. Maybe I can't hit something with an arrow because the arrow is always halfway there. But it's like, well, sooner or later it does hit it, right? So now we have all these kind of like Cartesian systems of, I can identify, here's an X position, there's a Y position, these have forces in those directions, and I can identify those forces and identify accelerations. Acceleration is dv dt, exact definitions. So that's why these are called kinematic equations, because it's like a solution to a specific dynamic, like kinetic problem. So now we have like just motion identified. So kinematics is all like, another thing for it is called geometry. So kinematics is all about like defining motion and observing motion, like and vice versa, right? Like if I know position and I know positions over time, I know velocity, because velocity is the change in position. All right, so take a second. Either you can think about it, like draw deep into the collective conscious, or access the collective unconscious online of something. Like, what is kinetics then? If kinematics is all about identifying motion, what is kinetics? Because these are two things that we have to use in the class. What is kinetics? Yeah.
Applying that motion to specific situations.
Applied motion? Wouldn't that be like a projectile? Would that be like
other situations that can't be described by those situations?
Okay, so different things that are not projectile motion. I think then we're talking about like different applications of kinematics. There might be cases where that's true. Yeah.
Like the transfer of kinetic energy,
Transfer of kinetic energy.
or like
Okay.
potential into kinetic.
Ooh, potential kinetic energy. Because kinetic is kinetic, right? Energy in motion. Okay, I like these ideas. Energy. Good kinetic thing.
Applying the theory of kinematics into real life kinetic problems.
So applying kinematics. So like carrying an accelerometer with you and measuring acceleration.
Yeah.
Yeah.
So kinematics is like the generalized theory of everything, right? Like we understand in theory how things are going to work. Kinetics will be, well, if something is working, how do we apply the theory to this exact problem?
So kinematics. So you think like theory versus applied kinematics? Something? Oh, sorry. Was there another?
Just like that's like for example, is like check out the two trajectory versus kinetics being forced to act on object.
Okay, so forces. All right, so we had forces, we had energy. And then both kinematics and kinetics are pretty like theoretical. Like you can build a whole sort of like just, I mean, it's applied, but it's like metaphysics of like, this is what I think is going to happen. But I do like the idea of like, maybe as engineers, we're like going one step further. Sorry.
Is it the relationship between multiple forces?
Relationship between forces? Yeah, maybe something. Yeah.
I was wondering if it had something to do with maybe objects moving in like more of a set path, flowing through something, or like kinematics
Okay.
has more freedom in the movement or something.
So kinematics, like, So kinematics is always like some kind of observation or definition of motion. And then, so we identified like forces are definitely a kinetic thing. Like if I'm identifying forces, I'm identifying kinetic things that are, yeah. And then same thing with like energy. When energy is changing in a system, now you're talking about like kinetic changes. Sorry. Yeah.
Kinetic usually has like acceleration in one direction, and like a constant acceleration, and kinematic is like changing acceleration. Or not kinetic. Kinematic is like acceleration in one direction. Kinetic forces changing acceleration or acceleration in multiple directions.
Well, at least for projectile motion, that's the case. Yeah, but you could have projectile motion near a black hole, where now acceleration is a function of gravity, and now, yeah, things start getting real weird real quick. But you would still have like kinematic equations that are describing like, here's the motion of my thing, and this is when I'm never gonna see it again, or I'll see it forever. Yeah, I think like as it's going into the black hole, you like see it, but it's actually gone because the light can't escape anymore. Anyway.
If kinematics defines motion, maybe kinetics describes that, or like why it occurs?
Yeah, so like kinetics is like the general description of like why did this motion occur. So, and that's why like a force is kinetic, because why did this thing fall? Well, because of gravity. Gravity is the kinetic thing that pulled the thing down. Same thing with like, or if you're pushing on something, it's like, why is it moving? It's like, well, I'm pushing on it. There's a force creating that motion. So this is sort of like the how motion occurs. And that's generally how we split up the two ideas. It's like we have motion. Sometimes we can identify, like we can see motion, but we don't know how to describe it, and that's okay. We can use kinetics and say like, all right, well, I know it's moving, I just don't know how it's moving. So let me identify what forces could be there, and then we'll math our way through it of like get to the point of like, that's why it's moving in a circle. There's like a tension acting on it, and the tension won't let it move forward, but it's trying to, so instead it moves in a circle. And now we've identified kinematics and then kinetics. And then there's one big unifying equation for kinetics and kinematics. What do you think that one is? In the last 30 seconds of class. This one everybody knows. You have nightmares about it. F equals ma. A is our kinematics. F is our kinetics. F equals ma. So we have cause and measurement, like things that happen. All right, cool. Thanks a lot.